So in order to find Waldo, the first thing we need to do is to understand a mathematical construct on images and on other type of signals as well, that is called convolution. It's a pretty simple concept, and it's essentially a dot product. There's nothing more to it. So some people have difficulty understanding it, but I'm going to take a very simple approach to help you understand what it actually does just to a given image. So let's say you've got an image, an input image over here, and we call it I. It's essentially a matrix, right? So we have these pixel values. Let's say we have got a pixel value over here that is 0, then we've got a pixel value over here that is 1, and so on. So this is the underlying image or pixel representation of an image, right? What convolution does is that it shows how a function, in this case an image, is modified by another function or another image. So let's say if we have a small filter, some people call it kernel as well, but to avoid any confusion with the kernels that we use in SVMs, which are completely different, I'm going to use the word filter over here. Let's say we've got a filter like that looks like this. Just like image filters, if you put your sunglasses on, the image of the world changes, right? And it's the same thing. We've got a filter over here that we call a kernel. Let's say if the filter has a certain type of shape or has certain pixel values, let's say we've got 4 over here, there is another here that is minus 4, then the convolution, more precisely the correlation of this kernel with the input image is defined as follows. What we do is that we overlay the kernel or the filter on top of the original image at one position. Let's say we do it over here, and we do a product. Let's say if I overlay the filter I have at this location in this image, then what I do is I simply multiply the corresponding, or do a dot product of the corresponding pixel values of the kernel with the image. And if you multiply 0 with 4, so this is 0 is going to be multiplied with this 4, this 1 over here is going to be multiplied with this 0, this 2 over here is going to be multiplied with minus 4, and then what we do is we sum all of them up. So it's a sum of products, or a dot product, right? And what that yields is a number, a single scalar value, which is minus 8 in this case. And what we do is at the center location of where we've overlaid the filter on top of the image, at that location we are going to put this particular image, this output, which is minus 8. So convolution or correlation in this case is an operation that takes an image as input, takes a filter, which is another image, as input, and outputs their dot product. So the output is another image, but we move this, or we scan this filter across all possible locations within the image. So let's say if we take a dot product of this, the value that at this location, we get a value of minus 8. Then what we're going to do is we're going to slide this filter over by a stride of 1, and then this filter is going to move at this location, right? So let me use a different color here just to make that point clear. Let me use, let's say, purple. Okay. So what we're going to do is that we're going to move that particular filter one location over to the right. Okay. And then we're going to do the same thing. We're going to multiply this kernel or this filter with the corresponding pixel values. So this time 4 is going to be multiplied with this 4 is going to be multiplied with this 0. This 0 is going to be multiplied with this 0. And then we get this minus 2 multiplied with this minus 4, which is going to yield minus 8. And then we are going to do some of these products. And then whatever value that comes out, let's say, I'm making stuff up here. Let's say if it comes out to be minus 10, we're going to put that number in the output matrix that we're creating. And then we're going to take a stride on the right until we run out of, or run into the border region, in which case we are going to move down, and then we are going to continue this operation. So there is going to be a double loop in this computation, and if we mathematically write it, we can have a double summation. And what we are going to do at each location, we're going to do a dot product of the filter that is given to us with the image that we have, and we're going to produce a new output image. That is how this convolution works. I just want to give a subtle warning here. The operation that I described, in which we are doing a direct multiplication of a given filter with a given image, is technically called correlation and not convolution. There's a subtle difference, but for our purposes, it doesn't really matter. The objective of this is that we have an image as input, we have a corresponding filter. That filter, when applied on top of that image using this operation that we just discussed, is going to yield another image at the output, right? And that image is going to be a processed version of the image that was given to us as input. So this is the mathematical relationship. This is the operation, the convolution operation. We go from all rows and all columns, and then we do a product of the filter of all pixel values in the filter with the pixel values at a corresponding location in the image to yield a particular output in the image. Okay, so that's what this operation does. Let's see what is the effect on when we do it for a real image. So let's say we've got an image like this, right? Like this one over here. If I multiply or if I correlate it with or convolve it with this particular filter, then it's not going to change anything. This is what is called an identity filter. Let's take an example over here. Let's say we've got this image as input. This is our filter over here. And let's try to apply the correlation operation on top of that. So if we apply it over here, we can see that once we place this whole thing over here with this as the center pixel, so if we put it over here, we can get 1, and then you can have all the other things are going to be 0, so you can get a pixel value of 22 in the output. If we keep on moving along that road, we're gonna get other pixel values. And since there are some border artifacts in this case, because the location where I overlaid this particular filter on top of the image, there were no pixels there for this particular row, right? So typically what we do is we take the borders into account, and if we take the borders into account, then the first location where I can put this filter is actually this highlighted red region. And that's why the output image is going to be slightly smaller. To be precise, it's going to miss one row. And it's going to miss one column, but that's going to be pretty much it. If we place this filter over on top of this particular image, then this is what we get. This 5 is going to be multiplied with this 1, and the rest of the numbers are going to be multiplied. We essentially get a value of 5 in the output. Then what we do is we shift on the right, and we get a value of 38. As you can see, there is not going to be any change. So the correlation of this input image with this particular filter is going to just give this thing, which is essentially the same thing with the borders missing. But other than that, it's not going to do anything. If we take a different filter, for example, if we take this particular filter over here and we convolve it with the given image, then what's going to happen is that at the central location, we are going to end up with the difference of these pixel values. These are going to be multiplied by negative signs in the original image, and then they're going to get added to these pixel values on the cross diagonal, right? So that is going to yield a different output, and to be precise, this is going to give you edges within the input image, and not any edges. It's going to give you these diagonal edges that you can see over here. So if you convolve this input image, this input image with this particular filter, the output that you get is this one. And you can verify why we have this by first of all doing it by doing some hand calculations, and also running some code which is really easy to run. All you need to do is to specify a given input image and the corresponding kernel matrix, and use this convolve operation from this, and you're going to get an output, right? So if you convolve this input image with this one, you're going to get these edges. If you use this particular filter, you're going to get these edges. If you change the filter, you're going to get other edges. So these filters can be very useful ways of extracting information out of an image. In this case, we use some precise filters that are already known to us. These are called edge filters to identify these edges, but there can be other operations you can perform on an image. Okay, so for example, if you want to smooth out the noise in an image, you can perhaps blur the image a little bit. So that can be achieved by simply multiplying or convolving that image with this particular filter. And this is simply at a given pixel value. What it's going to do is it's going to average out all the pixel values in the 3x3 neighborhood of that pixel, and that's going to smooth out any noise that you may have, and it's going to result in a smoother image. You can have different type of blurs, so you can have even larger blurs or blur kernels. In this case, this is a 5 by 5 matrix that when convolved is going to smooth out the image. And I welcome you to play with this with the code that I've given you over here and try to understand the impact of each of those filters. As you can see, if you have a pattern like this, like printed in a comic book, for example, those old comic books had these sort of pixelated patterns, or newspapers even. You can smooth out those effects by simply convolving this particular input image with these type of filters. If you do that in Python, it's really easy. You can have different type of filters. You can have identity filter, doesn't do anything. It just produces the same output. If you multiply a filter with convolve an image with a filter that is all zeros, you're going to get an all black image. If you have an edge detection filter like this one, you're going to get edges. You can do blurring. You can even do sharpening, and this is the kernel for that, or the corresponding filter for that. You can lighten an image, that is improve its brightness, by simply having a pixel value in having a kernel with a central value that is larger than 1, and that's going to increase every intensity within the image. You can darken an image by dividing. So if we have a filter that has a certain central value that is less than 1, in this case, since the filter size is 3 by 3, so we divide 6 by 9, which is the total dimensions of this filter, and we end up with a darker image. You can convolve with random kernels, and you can have those as different outputs. So convolution is a very important operation in trying to understand how these images are processed. So we have an input image. Just to recap, input image is convolve, which is essentially a dot product, and we result as at the output we get an output image. And this can be expressed as a dot product that I have seen. You can apply different filters. There are some really good image processing libraries. Let's say you can use skimage to apply different filters, but we are going to do something even more interesting with these filters. If you are new to this concept, I want you to spend some time trying to understand what convolution is and how we can get different outputs, how we can process images or change images by convolving them with different filters before moving on. Thank you.